Hey, 10th grade. Okay, today's we're going to be talking about kinetic energy, page 164. Okay, and don't forget to read pages 164 all the way to page 168. Okay, so first, let's define kinetic energy as a formula. Okay, kinetic energy is equal to 1/2 times the mass times speed squared. Okay, Ke, kinetic energy, equals 1/2 m times v squared. This is the formula for kinetic energy. Now let's learn how to solve this formula for m and how to solve the formula for velocity. So kinetic energy equals 1/2 mass times velocity squared. Let's solve this formula for mass. Okay, so first let's multiply both sides of the equation by 2. So we get 2 times the kinetic energy equals mass times velocity squared. Now we divide by velocity squared. So we get mass equals 2 times the kinetic energy over velocity squared. Again, mass equals 2 times the kinetic energy divided by velocity squared. Now, let's solve the formula. Kinetic energy equals 1/2 mass times velocity squared. And now let's solve for velocity. Okay, so we're going to do the same. First, let's multiply both sides of the equation by 2. Okay, so we get 2 times the kinetic energy equals mass times velocity squared. Now we divide by mass on both sides. So we get velocity squared equals 2 times the kinetic energy divided by mass. Now, square root on both sides. So we get velocity equals the square root of 2 times the kinetic energy divided by mass. So this will be the formulas that we're going to be needing for practice B. Okay? So kinetic energy, again, equals 1/2 mass times velocity squared. Mass is equal to 2 times the kinetic energy divided by velocity squared. And velocity equals the square root of 2 times the kinetic energy divided by m. So sample problem B says, a 7 kilogram bowling ball moves at 3 meters per second. How fast must a 2.45 grams table tennis ball move in order to have the same kinetic energy as the bowling ball? Is this speed reasonable for a table tennis ball in play? Okay, so here what we have. We have the mass of the bowling ball. So I'm going to call MB. Mass bowling ball is 7.00 kilograms. And the velocity of the bowling ball is 3.00 meters per second. Now, we have another mass, M tennis ball, I'm going to call it MT, is 2.45 grams. So this is equivalent to 2.45, 1, 2, 2.45, 1, 2, 3, equals 0.00245 kilograms. Okay, and we have to find the velocity for this tennis ball, table tennis ball. Now, we know that the kinetic energy for the bowling ball has to be equal to the kinetic energy of the table tennis ball. So by definition, we know that kinetic energy, right, is equal to 1/2 mass times velocity squared. So that means kinetic energy of the bowling ball equals 1/2 mass of the bowling ball, excuse me, times velocity of the bowling ball squared equals 1/2 mass of the table tennis ball times velocity of the table tennis ball squared. Okay? So let's find the kinetic energy for the bowling ball. This is equal to 1/2 times 7.00 kilograms times 3.00 meters per second squared. 3 squared, that's 9, times 7, and 63. Half of 63, that will be 31.5 joules equals, sorry, I forgot, to 1/2 mass of the table tennis ball times velocity of the table tennis ball squared equals 31.5 joules is equal to 1/2 mass of the table tennis ball times the velocity of the table tennis ball squared. So now let's solve for the velocity of the table tennis ball. So let's first multiply both sides of the equation by 2. So 2 times 31.5 joules, that's 63 joules equals mass of the tennis ball times velocity of the table tennis ball squared divided by the mass of the table tennis ball. So we get that the velocity of the table tennis ball squared equals 63 joules divided by 0.00245 kilograms. Okay, now let's find the square root of that. And we get that the velocity of the table tennis ball is equal to the square root of 63 joules divided by 0.00245 kilograms. So the velocity of the table tennis ball will be equal to 1.60 times 10 squared meters per second. Which is about 160 meters per second, right? Now, that would be this velocity of the table tennis ball. This has to be the velocity of the table tennis ball in order that the kinetic energy of the table tennis ball will be equal to the kinetic energy of the bowling ball. Now, is this answer a reasonable answer for a table tennis ball in play? No, right? It's way too fast. The speed is very fast for a table tennis ball. Okay, so that's we're going to be doing in practice B. Now, the solutions for practice B are the following. So these are the solutions for practice B. Okay, practice B, page 166. For problem number 1, velocity equals, or the speed equals 1.7 times 10 squared meters per second. Number 2, that's 38.8 meters per second. In number 3, you're going to have to find the first two kinetic energies. The first kinetic energy will be 2.4 joules, and the second kinetic energy will be 4.8 joules. And the ratio between the two kinetic energies will be 2/1. In number 4, it's very similar to number 3. The first kinetic energy is 2.4. The second kinetic energy, that will be 9.6. And the ratio between the kinetic energies will be 1/4. And finally, number 5, the mass will be equal to 1.6 times 10 to the third kilograms. And for the chapter review, we have problems number 19 and number 20. Number 19, the kinetic energy will be equal to 7.6 times 10 to the fourth joules. And number 20, the speed will be equal to 1.7 times 10 to the fourth meters per second. Okay, all of these problems, okay, you're going to be using the three formulas that we did at the beginning of the video. So this is your first assignment. Now, let's look at practice C. In practice C, we're going to be talking about the work-kinetic energy theorem. The work-kinetic energy theorem states that net work equals to the change in the kinetic energy. Okay? Remember that the change in the kinetic energy is equal to final kinetic energy minus initial kinetic energy. In other words, this means that net work is equal to 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Okay? So this is the work kinetic energy theorem. Also, keep in mind that in the beginning of the chapter, we learned that network is equal to net force times displacement times cosine of theta. Okay? Don't forget this, because it's going to be very helpful for this practice C, for the work kinetic energy theorem. Now, if we look at practice C says the following. On a frozen pond, a person kicks a 10.0 kilogram sled, given it an initial speed of 2.2 meters per second. How far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.10? So what information do we have? We know that the mass of the sled equals 10.0 kilograms. And we know that the initial velocity for the sled will be equal to 2.2 meters per second, right? Now the problem says, how far does the sled move? Okay, so we're looking for D. How far does the sled move? So how are we going to measure this distance? In order to find the distance, we must find how far the sled move until it it stopped. So when if the sled stopped, that means that the final velocity, it has to be equal to 0 meters per second. Okay, and we're they gave us that the coefficient of kinetic energy is equal to 0.10, right? Now we have our sled in the ice, right? We have the sled in the ice, and the sled is kicked in this direction, right? And we know that it has an initial velocity of 2.2 meters per second. And we know that if it has a, if they give us a coefficient of kinetic friction, that means that there is kinetic friction, right? And we need to find the displacement when the sled has a speed, a final speed of 0 meters per second. Okay? Now, we're going to be using the Work-Kinetic theorem. The Work-Kinetic theorem stated net work equals a change in the kinetic energy. Net work equals final kinetic energy minus initial kinetic energy. Net work equals 1/2 mass times final velocity squared minus 1/2 mass initial velocity squared. But we're looking for the distance. Here's where we said that we're going to use this formula for network. So we're going to substitute. Instead of writing network, we're going to write net force times displacement times cosine of theta. Okay? Equals 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. Okay? Now, in the given information, we found out that the final velocity was equal to 0. Since final velocity equals 0, we can cancel this. We're simplifying the formula right now. Okay? So we get net force times displacement times cosine of theta equals negative 1/2 mass times initial velocity squared. Okay? Now, net force. How many forces are being applied in this system? Okay? Now let's analyze the system. So if we analyze the system, notice that the sled is not being pushed, the sled was being kicked. So there's no force acting to the right side of the system. Just the only force acting on the system is the kinetic friction. This is making the sled to stop somewhere over here. So net force in this case will be equal to kinetic friction times distance times cosine of theta equals negative 1/2 mass times the initial velocity squared. Now from chapter 4, we learned that kinetic friction was equal to the coefficient of kinetic friction times the normal force times displacement times cosine of theta equals negative 1/2 mass times initial velocity squared. Okay, and normal force in this case the normal force equals to the gravitational force. Okay, y, remember, Fy, changing summatory of forces in y is equal to normal force minus gravitational force equals 0. So normal force equals to the gravitational force. And gravitational force is equal to gravitation equals to mass times gravity times displacement times cosine of theta equals negative 1/2 mass times initial velocity squared. Okay, so we're going to solve for d. So that means that we're going to divide everything by UK, coefficient of kinetic friction, times mass, times gravity, times cosine of theta. So we get d equals negative 1/2 mass times initial velocity squared over UK, coefficient of kinetic friction, times mass, times gravity, times cosine of theta. Okay. Now theta in this case, since it's going to the right, theta equals 0 degrees. Okay. So let's substitute. Sorry, the direction of the kinetic friction, since we're using the net force is for the kinetic friction, is 180. Okay. So now let's substitute. D equals negative 1/2 the mass, that was 10, times the initial velocity, 2.2 meters per second squared, divided by 0.10 times the mass, 10 kilograms, times gravity, 9.81 meters per second squared, times cosine of 180 degrees. Okay, so if we use our calculators, we get okay, let's see what we can simplify from here. We can simplify 10 kilograms and 10 kilograms, and that's it. So using our calculators, we get that D equals 2.5 meters. Okay, so this is what we're going to be doing in sample C. Now, for sample problems, practice C, exercise 1 and 2 and 4, you can do it on your own. Number 3, we're going to be doing it together. So I'll let you know when we're going to be doing this problem together, okay? So for practice C, you're going to be doing also practice C. So the solutions for practice C are the following. For number 1, 7.8 meters, you're going to have to find distance. For number 2, 21 meters. Number 3, again, we're going to do it together. Number 4, 3.0 times 10 to the second power newtons. Number 21, you're not going to do it. Number 21, for some reason, I don't understand why they did it in practice C. 21 is actually for practice D. We're going to be doing it in the next practice. And problem 22 is equal to 1.4 meters. Okay, so that's it. I'll let you know when we're going to be doing number 3 together. Okay, take care, guys. See you next week.